Hi, I'm Brian from Simply Brian Enterprises, and welcome to my channel. And welcome back to my studio. It's been a few weeks, but thankfully my knee is definitely healing up and I'm able to traverse the stairs a little easier. So I'm back in my studio and ready to record some more videos, which is a good thing because I'm horribly behind on my Pi Pico homework. Today's video, we're going to be looking at the homework solution for TopTechBoy's Raspberry Pi Pico class, lesson number 10 and 11. If you remember lesson 9 that I posted several weeks ago, we were taking the keyboard input to determine the brightness of the LED and then displaying that brightness on the LED itself. In lesson 10, we were challenged to move away from the keyboard and actually use a potentiometer as input. So if I flip over to my table view, we can see, first of all, I have a new table camera. I've replaced the camera that was with the wide angle lens with something that's more rectangular now, so hopefully that'll make this easier to look at. Still playing with focus and color balance and things, so the next few videos will look a little strange as I work on it, but I look forward to having a better table camera in the future. So what I've got here is I've just got a simple program running that is taking the input of the potentiometer and writing it as a value to the LED. And you can see when I move all the way to the right, it gets brighter. And as I move all the way to the left, it gets dimmer. And that should be it, right? That was the assignment? No, 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 no. We can see very clearly here the LED did not go off. And of course, the reason it didn't go off is because I am just doing a simple translation of the input of the potentiometer to the output of the LED. The reason that doesn't work is because the potentiometer will never be zero and it will never be the maximum value. So one way around this is, here I'm going to move this back to the center so we can see. One way around this is to use our minimum and maximum values. I used these in a previous program where I basically said the lower boundary is a number, in this case 500, the upper boundary is a number, in this case 63,000, and using this if statement, if we go outside of those values, we'll just write them as basically 0 and maximum. And when we run this particular program, we get the desired effect. Oh, here, let's By the way, welcome back to my studio. These next couple videos are going to be kind of shaky. I look forward to getting back into my usual routine of filming these next two. Forgiveness, please. So I'm going to go all the way up. And this time when I go all the way down, because once I drop below 500, I'm going to write it as 0, the LED goes off. So one would expect that I'm done with my assignment. I can just turn that in and I'm good, right? Well, I have a funny feeling that if I were in Paul McWhorter's TopTechBoy's industrial technology class in high school, I would be getting this assignment back with red pen written, "You skipped the math, do the math." So I think we need to go back and we need to do some math. So what we're going to do in order to do this mathematically is I'm going to take the output of the potentiometer, and rather than just writing that value to the LED, I'm going to convert it, and I'm going to convert it to a percentage. So when I'm all the way to the left, my percentage is going to be 0. When I'm all the way to the right, my percentage is going to be 100. And then whatever it is in between will be that percentage value. Then I'm going to take that percentage value and I'm going to write it out to the LED. So obviously all the way off, 0 is going to be 0%. All the way up, 65,535 is going to be 100%. And because I'm going to be using a floating point, it's going to be very accurate. So I have to start thinking about what is the math in order to do that. So we're going to go back to our slope intercept. And here at the low-tech, high-tech channel that I run, I'm going to be using these fancy index cards. My apologies. Did I mention the first few videos back are going to be a little shaky? Bear with me, they'll get better, I'm sure. So I'm taking my input from my potentiometer, and when I'm at 0%, I'm reading 500. When I'm at 100%, I'm reading 63,000. And when I break that out, so I do y2 minus y1, x2 minus x1, I end up with 625,000 over 100, 625, or I get this equation of y equals 625x plus 500. There's one problem with that. Did you catch it? Typically, when you're doing these, you know the x value and you're looking for the y value. In this case, because I'm taking input from the potentiometer, I know the y value. I need to solve for x. So I need to do a little more math to make this equation work. So I'm going to substitute in, for y, I'm going to substitute in pot value. For x, I'm going to substitute in percent. And now I've got to start solving. So this number 500, I don't want to use the actual value 500. I want to use pot min because that's where that 500 comes from, and it could change between programs. So the first thing I'm going to do is I'm going to subtract this 500 or pot min from both sides. So I've got pot val minus pot min equals 625 times percent. And then I'm going to divide 625 from both sides, which is pot max minus pot min divided by 100. That's how we got that 625. And what we end up with is, we end up with this equation, pot val minus pot min over pot max minus pot min times 100 gives us the percentage value. Now writing it back is a lot easier because I'm going to be starting at 0. So if I were to do a point slope like this, it would just be a line from 0, 0 to 165, 535. So I don't have to do quite as much advanced math. I can just simply take 65,535 over 100 times my percent value and write that out to the LED. And so if we look at the code to do that, I'm going to flip over here and take a look at this code. And here I've got my minimum and maximum. And I come down here. And again, I'm setting my boundaries, but this time I'm setting it to pot min and pot max because I'm going to do the percentage calculation. So even though I'm going to move it, even though I'm going to move this potentiometer all the way to the left and it's going to register 0, or I should say a value of 500, I want that to send 500 to this equation. There's the equation. Okay. I don't want to force it to 0. So here's my equation written out: pot val minus pot min over pot max minus pot min times 100 into a floating point value so that we get that percentage out as a float, into my percentage, into my pot val percent. Then I'm going to write it back out. Again, this is an easy one because it's just 65,535 divided by 100 times the pot val percent. Write it out. And we're going to print this out so that when I run this, and I'm going to just, so first of all, I have a program running, so I need to stop that first. And I'm going to start it. And now we can see we're outputting the actual potentiometer value, the percentage, and the LED output. So if I turn this all the way to the right, we can see that I'm doing 63,000 on the potentiometer. We're not going to go above that value. And that's converting properly to 100%, which is 65,534.99 because there's floating point math. We're going to say that's close enough. And so I'm going to start backing this off now. And what I should see when I get, we'll see how close I can get to 50% here. That's pretty close to 50%. We can see that our potentiometer value is just slightly less than the LED value, which is exactly what we'd expect because of our ranges being clipped off. And then if I turn it all the way to 0, we can see the potentiometer is reading 500 because that's its low point, but we're taking a percentage of 0 and then writing a 0 value to the LED. So that is, I believe, the correct way that Paul McWhorter would say, yes, that is the proper way to do the math. That is the proper way to do the translation. Then there's just a little bit of extra credit here. All I'm doing is I'm taking this, this percentage value and I'm just splitting it out among the 4 LEDs. So I'm taking, basically trimming off, I've kind of shown this before, but I'm trimming off the first 16,384 and then just kind of walking my way through. Um, I'm not going to narrate all of this code, but you can kind of see what it's doing. It's basically stepping through depending on what that output value is. And so when I hit go on this program, we can see there's the output again. So I'm going to start it. I'm going to start turning it up. You can see our percentage is 4%, LED 1, we're starting to get some output on. And now when I approach 25%, we should start seeing the next LED start to come on, and we do. And then we just keep going, and now we're going to get close to 50%. And we see LED 3 start to come on, and then all the way up to 75% and 4, and all the way to 100%. And now you can see potentiometer 63,000, percentage is 100, and you can see all 4 LEDs are running the maximum of 65,535. So that is the conclusion of lesson number 10. Now in lesson number 11, it was pointed out to us that there is a discrepancy in how these LEDs are displaying the output. We are sending it a digital value that is linear. However, the way these LEDs display looks a little more exponential. So what we need to do is we need to make changes to our output to accommodate the fact that, well, here, let's go. Let me start this up so I can show this a little better. So as I increase the potentiometer, you notice it gets really bright the first 50% or the first halfway. And then as I increase, it doesn't increase as much. A lot of that increase is on the lower end of it. And that's just because the LEDs have a tendency to display in more of an exponential fashion than the linear fashion. So what we have to do is we have to think about this exponentially instead of linearly. So the way I've done this in the past, and I'm going to do it here, is I'm going to use a logarithm, because a logarithm is basically a 0 to 10 value, and it makes just kind of the mental gymnastics of trying to make this work a little easier if we're using numbers like 0 to 10. So if you imagine the potentiometer laid out like this, all the way left is 0, up and down, straight up and down. Where's my hand? There it is. Straight up and down is 5, and then all the way to the right is 10. We can kind of think of it that way. Now, if we look at the log values, so if I take a log of 10, I get 1. And then if I multiply that by 100, I get 100%. So that makes sense. But if I take a log value of 5, which is straight up and down, I would expect that to be closer to 0.5, but it's actually 0.69 times 169%. So that's how we can see, as this is increasing, as I move it to the center and straight up and down, I've already gone 69% of my available brightness, not 50 like I'd want it to. So the way we account for that is we take the value of 10 and raise it to basically our step value or our percentage value, and then we're going to do some translation. So we take 0.5, which is 50%, so 10 to the 50% equals 3.16 times, that's 31%. So that tells us that we are going to have the output value, instead of being, when I go all the way up here, the value being sent 50%, which is going to give me 69% of brightness. Oh, you got to think about that a second. 69, if I go halfway, so if I move to a position of 5, that's 69% of the brightness, even though my output value is only 50% of the output. I'm going to translate that 50% of the output to 31% of the output. 25% is going to get translated to 17. 75% is going to be translated to 56. And so what that's going to do is that's going to give us a much more linear look, because as we go up, it's going to do a slower increase on the lower end, and then as we move up, it's going to get faster again because it's more of an exponential. So the math behind this, it's a lot of work, but I'm taking my pot val percent divided by 100, so that way I'm converting it back into a decimal format like I had here. I'm converting it back to a decimal format, raising 10 to that power, and then multiplying by 10. So basically taking, in this case, if the percentage coming off the potentiometer is 25%, I'm taking 10 to the 0.25 times 10, which we know is 17, and that's my log val percent. Then when I go to write it out, it's going to be LED value. Here's again my 65,535 divided by 100, so that's just my simple percentage. But then I'm going to multiply it times that percentage to get the factor of how much output we're actually sending to the LED. That might sound like a lot of work because it is. However, we do get the desired results when we run the code. So I'm going to scroll down here a little bit. So I'm doing my simple percent first on the potentiometer. Then I'm going to convert that to my exponential output. So in the case of, let's say that this value is 50%, this value is going to come out to that 31% that we're going to use as our factor. We do hit a corner case because anytime you take a number and raise it to the power of 0, it becomes 1. So we have a case where even though the potentiometer, our percentage is 0, when we're done doing the math, it's going to come out as 1. So we have to factor for that, and we have to take that corner case and we have to omit it. Now in this case, we're multiplying by 10, so our corner case value is 10. Only 10 will have this problem, so I can make a simple if statement. If we run through the math and the output is 10, we know that that value is actually supposed to be 0. Then we come down here, and again, we do, just like I showed, we take that percentage value, but now we're going to multiply it by this multiplier up here, or whatever our factor is, to get that right. And then we're going to write that out. And once again, we're going to write to the screen. So we're going to see what these values actually are. So here I'm potentiometer of 500. I'm going to go and let's go to, as best I can, 50%. And we can see that my potentiometer value is about 32,000, which if you think, okay, 62,500, so half of that is about 31,000. So when I'm at around 50%, I'm really close to 31,000. That makes sense. But then if I take the logarithm of that value, that 31%, what's 31% of 65,535? Quick in your head? No, I did it for you. It comes right around 21,000. So what we see is that I've got a potentiometer value of 31,000. I'm running it through my exponential math, and then I'm outputting it as 21,000 essentially. And what we can see is as I increase, we can see we get a lot brighter on the second half than we did before. So that was kind of the long way around, but I did want to show you that. One question did come up, and there was some discussion about it, about whether or not it matters if you use a larger number. So I used 0 to 10. I think Paul used 0 to 16 and then showed us again the math using 0 to 50. So the question is, what happens if you use 100 or 1,000? And the general consensus is it really doesn't matter that much. And one of the reasons, especially with my code, that it doesn't matter so much is because I'm doing everything as a floating point value. So regardless of how big this number is, whether, if I turn it to, let's say I use a scale of 0 to 1,000. So I'm going to spin this up to 500 in the center, and then I'm going to do all the math. Do I get a smaller number, or do I get, a more precise number? And the answer is really no, because I'm using a floating point, and you saw when I ran the code how many decimal places it went out to. It really doesn't matter if I'm using 0 to 10 or 0 to 1,000. It's going to be roughly the same effect. So hopefully you enjoyed this video. Thank you for watching. Looking forward to the next lessons where we get into the RGB LED, pulling out the Kepler kit again. Really looking forward to it. Hopefully you'll join me for that journey. For Simply Brian Enterprises, I'm Brian. Thank you for watching.